Welcome back to the American Ceramic Society's course on firing of ceramics. We're in unit number 2, and in this unit, we've spent some time getting fuel into the furnace so that we can release energy into the furnace atmosphere so we can accomplish the sintering operation that we have chosen in processing our product. There was a lot of time dealt with getting fuel through regulators, through valves, into ratio regulators in order to get the right amount of fuel proportioned on ratio with the right amount of air. In most cases, the air drove the gas in terms of volumes of both, and so we were able to maintain that ratio. Later on, we found that there were special kinds of combustion systems called step fire or pulse fire that could accomplish firing with some energy savings. So today, we're going to the next component of a kiln, and that is to look at the refractories, the insulation in the kiln, because we not only have to contain the heat, we also we not only have to provide the heat, but we obviously have to contain the heat. And if you get above a few hundred degrees Fahrenheit, we're not going to be able to use carbon steel. In order to contain that heat, we're going to have to insulate it so that we can go to much higher temperatures. So you remember that the difference between the past world and the modern world is that we can really concentrate energy release into a confined area called a kiln. And of course, in the modern world, we have refractories that can do miraculous things. So we're going to talk about that. We're going to talk about the energy storage and the energy loss. So we're not really talking about the energy into the product to create sintering, because that's a fairly small amount of energy usually, unless there's an unusual endothermic reaction, a reaction that takes energy. So where we're going from here is to go into some kiln simulation, as I call it, and some modeling to see how the eSolutions program works. But before we do that, we have to talk a bit about refractories. Just a moment of review. With solid fuel combustion last time, we talked about modern systems that use pulverized solids, and we convey those to burners in the kiln. This material is usually injected or dropped by gravity into the kiln and burns using the air coming down the tunnel in the kiln. We don't typically inject air and solid fuel together. Part of the reason for that is there's always a dust explosion hazard when we start mixing air or oxygen and solid fuels. So we've learned to be very careful and apprehensive about dust explosion potentials when we have combustible particulates that are in our system. Now, we talked a bit about the mechanism of combustion, about the fuels burning as they drop by gravity into the kiln environment. We talked about the influence of the ash on the refractories in the kiln, the insulation in the kiln, and on the product. And of course, because of the ash, we typically can't make glazed products in solid fuel fired kilns. A lot of people consider solid fuels to be dirty fuels, but because of the ash, the fly ash that can result from combustion that can be conveyed out into the atmosphere, hopefully captured in a dust collector. In addition to the dust explosion potential, we also talked about some of the health and environmental effects of fuels. We talked about respiration of fuels and the fact that ash was in a particle diameter that typically can pass into the lungs and can be captured into the lungs and cause human beings some problems. We talked about my personal opinion about smoking and dust exposure. We talked about a little history of people that worked in solid fuel kilns back in time and had to deal with some issues later in their lives. And we talked about the environmental effects. So I hope the safety aspects of solid fuels was a particular interest and got your attention. Okay, well, let's talk about refractories. The word refractory means that something does not change. In the case of kill linings, the internals in kills, we don't want these refractories to shrink as they are increased in temperature. You can apply the word refractory to other things like human beings even. If a person doesn't change their opinion ever, then you could call them refractory. But in our case, we're only interested in the thermal response of the insulation and to make sure that this insulation does not shrink at the temperature where we're using it, because shrinkage causes all kind of difficulties. It increases the density of the refractory in situ in the wall of the kiln. If that happens, then we've lost some of the insulating ability. We might have opened up joints and have air leaks. So a lot of things can go wrong when refractories shrink. And usually refractories are defined in terms of a duty rating, a use limit for that refractory, and that is determined by a maximum amount of shrinkage that a manufacturer will allow a refractory to exhibit at a particular use temperature. And usually that amount of shrinkage is less than about 1.5% or even lower. It depends on the refractory. Refractories not only have to insulate, they have to support the load. They have to be rugged so that they can survive plant conditions. They have to endure thermal shock situations. Usually the heating rate on a kiln is determined by a maximum rate at which you will not thermally shock the refractories. Of course, you don't want to thermally shock your wear that you're firing. So refractories are subject to mechanical damage. They can be subject to reaction with the kiln atmosphere, corrosion in the case of ash, and shrinkage. So I'm really going to use the word kiln liners to talk about thermal insulation. And just to get you started thinking about this, we have several types of refractories. You've seen these pictures before, but typically in the shuttle kiln, you can see the bricks that constitute the lining and the deck on the kiln car to support whatever's being fired. And you can see in this kiln, there's a typical arch shape, which you will find in the roof of many kilns. Modern kilns sometimes have flat suspended roofs where the refractory bricks are hung from above the kiln to constitute a flat lining. So these are typical bricks in this kiln. They're probably hard bricks. In my small laboratory kiln, we have insulating bricks that constitute the lining in the kiln. And you can see that the load is supported on a refractory sagger right here. Also in my laboratory, there's a larger kiln which has ceramic fiber modules that constitute the lining. You can see these, and then the load is supported in this kiln design on a refractory deck block. So the load can be placed there. The car, of course, is slid into the kiln and the door shut and the kiln is fired. So refractories constitute several types, and usually they are made of minerals found in the earth, oxide materials, not always. There is a lot of silicon carbide used in kilns in various kind of supports and things of this nature, but usually they are aluminosilicate materials, and then they have a duty rating, and they include hard bricks. Hard bricks are the older type of lining design. They have some advantages, which we'll talk about. There are castable refractories. These are refractories that are mixed with water and cast like concrete. They're refractory concrete, not Portland cement concrete. Castables contain calcium aluminate cement as the binder, not calcium silicate cement. And so castable refractories act a lot differently because of this calcium aluminate cement. We have insulating products like insulating fire bricks. They all have a duty rating, and we have fiber refractory products and some other things that go along here, but the fibers are perhaps a more recent invention. Their great advantage is that they limit the amount of heat storage because of their light weight. And of course, they have incredibly good insulating values. So there are different classifications. I'm not going to say every word on these slides, but we have classifications in North America and Europe for hard brick, for insulating fire brick by duty rating. Plastic refractories, sometimes these are called moldables. Moldables, they can be shaped. They're not used so much in ceramic plants, but they are used in other industries quite a lot, and they have the advantage of being able to use fairly quickly, where castables, when they are applied, they must be allowed to set. The cement is sensitive to temperature and cleanliness of the water, for example. And so each of these types of refractories is given a duty rating, which is based on PLC. Now, PLC means permanent linear change. So that means the refractory is heated up to a use temperature, and its linear change percentage-wise can only be a maximum, in the case of castables, 1.5% at the rated service temperature. Up here, insulating fire brick have a maximum PLC in Europe of 2% in 12 hours. 12 hours. It's very important to know what this duty rating means. 12 hours, where in the United States, hard brick with a PLC is typically a maximum of 5 hours at the service temperature, whereas insulating products are 12 hours or more. So it's very important to understand the basis of what these duty ratings are. Here's some more on hard brick. In North America, we have classes by alumina content. Okay, so most ceramic plants are using 60% alumina or less if they use hard brick, or they're using a fire clay. Fire clay bricks are the typical type of bricks used in a fireplace hearth. They're yellowish, brownish in color. They have different ratings: high heat duty, super duty, depending on the thermal exposure. So they have a density, a porosity, of course, and strength. Bricks are very rugged, and people without, how should we say, the most extreme skill levels can lay bricks, and they're good for patching. So even though they're older fashioned types of products, they have some important attributes of being able to be used right away. Now, bricks have properties, and you will see this. I've listed one fire clay brick, another fire clay brick, and a 60% alumina brick based on a very alkali resistant aggregate called andalusite, whereas these are fire clay based. They all have densities. You can see porosities, and most of these bricks are pressed. So they're going to show about 16% porosity or thereabouts. They have crushing strengths, which is important for load bearing. And of course, they have high temperature properties, and they have tolerances on dimensions. Now, in addition to being laid against the wall, sometimes against the walls of furnaces, there are clips or other devices, anchors that hold them against the wall, particularly for a very tall furnace, but especially in the crown or roof of a furnace if a refractory is used here. Here's a steel hanger going around a pipe in section with a brick anchor that protrudes through the thickness of the refractory lining, and they're showing refractory material, castable or plastic, being formed around that brick anchor, holding that crown up. In some ceramic plants, particularly tunnel kilns, this anchor may form a T at the base. It may be wider at the base so it can hold up tile between adjacent anchors. The theory of this anchor is that it holds the refractory hanger brick in compression, right where it's holding on to it. I've seen some cases where other systems were used to suspend a hanger tile through a flat suspended crown, and they put the brick in in tension, and they put the brick in tension when it's in use, and there have been some failures in that situation. So the old-fashioned system is to put a hanger up here that's going to hold that brick just at the top in compression. Now, castables are a little bit different. As we said, that they are based on duty rating. There are a lot of things about castables that are sensitive. For example, they're sensitive to the cleanliness of the water. Okay, acidic waters will delay the set of calcium aluminate cement, whereas Portland cement and normal concrete is very forgiving of conditions. That is not true of castable refractories because of their calcium aluminate cement. Here's an example. It's maybe not the nicest example in the world, but nevertheless, I was mixing some castable one day in a paddle mixer. The company that I was working for wanted me to help them develop best practices for making precast shapes. So I was out with the lab guys and the production guys, and we were making precast shapes and writing down the best thing to do, the procedure. And so one of the supervisors from production came over and said, "I can kill that castable." I said, "What do you mean?" He said, "I can kill that castable." And so he said, "I'll bet." Well, I knew what went into the castable, and I said, "Okay, you can't go anywhere and do anything. You got to stand right here and you got to kill it in front of me." So what he meant by killing the castable is he could prevent the castable from ever setting. So I took the bet and I lost the bet because that plant supervisor took a sweetened beverage, sugar sweetened beverage, a soda, and poured it in the form where I was packing the form with castable, and it never set. Came back the next morning and I had to pay up because it never set. So sugar is one of the ways that you can delay setting of castables. Other organic liquids can do that. Nevertheless, we know that they're insulating castables, and those are typically less than 100 pounds per cubic foot or less than about 1.6 grams per cubic centimeter. They're hard castables for load-bearing applications that are generally greater than, supposed to be 120 pounds per cubic foot, or greater than about 1.9 grams per cubic centimeter. So we have insulating castables and we have lightweight castables. Lightweight obviously used for insulation, and dense castables used for facing of furnaces, furnace hearths if they're used for that, arches and things of that nature. Now here's some work I did a few years ago that looked about the water addition, and the same castable material. I just varied the water addition. You can see more water, the cured density and the dry density went down. You're separating the particles by adding more water, aren't you? And look at what happened to the modular rupture. It went dramatically down as you added more water. So usually the guys that mix this up are general laborers, and they realize pretty quick that if they're mixing in a paddle mixer, that the more water that they add, the easier it is to get it out of the mixer. And so they think that's not going to hurt the material. It's going to harden up and it's going to be pretty good. Well, it's not going to live as long because if you use the manufacturer's recommended water content to get the right water to cement ratio, it's going to be harder to get out the mixer, but it's going to be a much more durable material. Now, it's important for me to talk a little bit about some safety notes. In cold weather, or if the pH of the water is a little bit acidic, it can look like a material has set up when it really didn't. It can give a false set. It might be frozen, for example. And so when you begin drying out the furnace, preheating the furnace to dry out that castable, which is always recommended, that castable can experience explosive spalling, steam spallation. You remember that from the drying course. So occasionally someone is killed by this in a large industrial furnace. All the manufacturers say you have to protect the castable from freezing. You have to use material in casting that's above the freezing point of water. And you have to cure that castable for a certain period of time under certain thermal conditions before you ever put any heat on that material. Otherwise, you can have this explosive spalling phenomena. So it's important for plant people to understand that what they do really affects their own safety and affects the durability of the material that you're using. Okay, well, hearth deck blocks. Here's my friend standing in front of the hearth of a tunnel kiln where there's a fairly low setting here. These kiln was making paving brick. Here's the hearth of my laboratory furnace, and you can see it's fiber on the bottom, so there are posts sticking up and holding these deck tile on top with posts and beams, and then the deck tile spanning the distance across between the beams. So these products are typically cordierite-like compositions, low thermal expansion compositions, trying to minimize any thermal shock damage because they're heated up and cooled quite a lot. In higher temperature kilns, meaning higher than you can expose cordierite to, they may be high alumina products or silicon carbide, something of this nature. One thing that happens in these kilns is that dust accumulates on the car deck. Okay, it's not such a problem in a laboratory kiln, but in a big production kiln like this one, dust accumulates and it works its way down between the deck block, and that's called joint packing. Okay, it's well known in various industries that the particles make their way down into between the joints in the deck block, and in effect that makes the deck expand. Okay, because you've opened up the joints, and you can actually have a situation where the cars won't push. They're running into the side of the kiln, or factories are. So a lot of people are using vacuuming systems that employ robots to clean their cars after each use so that they don't have this problem of joint packing. Okay. Mortar, the one that I used a lot, Saerset 3000 degree mortar. There's some things that need to be said about it. The first thing is that it's a wet mortar. It can be purchased in dry form as well that you mix at the job site. These wet or dry mortars contain sources of sodium silicate, water glass, and that's the binder. And water glass notably is an eye burn hazard. So your personnel need to know that they don't need to stick their finger in the mortar and let it splash and stick their finger in their eye or let mortar splash in their eyes. It's going to burn, and you flush it with clean water immediately when that happens. If it's a prepackaged wet mortar, you're going to open the can and there's going to be some water separation. It looks like a dark oily liquid is on the top. You simply remix it in the can before you use it manually. It's not an easy job to manually remix it with a trowel. Another thing to be said is you shouldn't dilute these mortars with water because if you do that, it's going to lose its binding capacity. So refractory mortars are used as thin set mortars, very thin mortar joints, not like masonry mortars used on buildings, which are typically 3/8 of an inch. These mortars are typically dip joints that are very thin, on the order of a few millimeters thick. Now, some of you are using, especially in older kilns, some kind of bulk insulation, which might be vermiculite or perlite, which these are natural minerals. Expanded perlite is very good insulation. And you might be using a bulk ceramic fiber or mineral wool, or even some kind of refractory grog for insulation. So all these materials can provide some respiratory hazard. Then there are insulating fire brick. There are two types generally available in North America. They have a duty rating based on 24 hours of shrinkage. Okay, I'm going to talk more about that in just a minute. But one of the types, which is a little bit lighter in color, can be susceptible to potassium vapor in solid fuel fired kilns. It may cause expansion below the surface and cause spalling. This takes a long time. The other type of insulating fire brick is a little darker in color, more yellowish, like a fire clay brick, and it can shrink in a sawdust fired kiln. So these are just examples of two different products. I'm not aware of the types of products used in the rest of the world, but you need to be aware of the fact that these different types of products behave differently in kilns. And then, of course, there is ceramic fiber. Ceramic fiber is sold in blankets or folded and made into modules that can be inserted into the kiln wall with an anchoring system. They have a duty rating and exhibit shrinkage and service, especially if you exceed the duty rating. They can devitrify or become crystalline. They're glassy fibers when you buy them, but in long exposure to high temperatures, they can devitrify and then they become fragile and dusty. And they've been studied for health effects for a long time. Respiratory protection is usually always recommended. So here's the difference between a ceramic fiber blanket. You can see the blanket being unrolled there in this example. And when these products first came out, they were laid like wallpaper on a wall and anchored to the wall, but it was found that this type of construction was susceptible to tearing of the fiber, especially when there's draft imposed upon the fiber. And so the modules were invented. And so these are pre-folded blankets that are strapped with plastic strapping. Sometimes there's an anchor built in to anchor it to a wall. And literally, people without much skill can anchor those to the wall. I'm not saying that refractory masons and others don't have much skill, because they have a lot of skills that I don't have. I'm just saying that it's a relatively easy situation to deal with. Modules and individual fiber. Individual fiber rolls are used a lot for plugging leaks around furnaces, and there are spray materials that you can spray in for the same purpose. Now, I tried to look at the basis of the duty rating, so I looked in ASTM standards, and here's a paragraph 7.4 from the C892 standard in ASTM. And you can see here's the basis for a duty rating, and it depends on a linear shrinkage criterion that people can set after reheating for 24 hours. Remember, the European standard was 12 hours. This one's 24 hours. So I told you I was going to tell you a little story, and here it is. One time I'm sitting in my office at the university, and I get a call from one of my research supporters. They were about 100 miles away, so it's a pretty good distance. And they said, "We need you up here." We just took our kiln down for annual maintenance. It had a brand new kiln lining of fiber refractory in it. And after 50 weeks of operation, cracks developed around the refractory lining, particularly in the crown of the furnace. Well, that's where it's hotter, right? So I went up there and I walked down through the kiln with a spotlight and looked up and looked at the cracks, took some pictures and stuff, like I knew what I was doing. And then we walked out for the inevitable meeting in the plant manager's office, and he said, "We're going to sue those guys. You know, we put up a 2,000 degree insulating material, rated insulating material in the crown." I said, "Okay." And I said, "What's your firing temperature?" They said, 2,000 degrees. That was Fahrenheit, of course, United States. And they said, "We're going to sue that manufacturer and they're going to have to pay us." And I said, "You're going to lose. You're going to lose." Well, we live in a litigious society in North America, but I said, "You're going to lose." And that made the plant manager pretty mad. And he said, "Why?" I said, "Well, the 2,000 degree duty rating was based on 24 hours of exposure to 2,000 degrees. You've been operating for 50 weeks, right? So it's normal to expect some shrinkage at this extent of time. So you're going to lose." So eventually they called up the manufacturer and they sent some repair material up and everybody was happy. Now I have a slide of a constant called thermal conductivity. It's actually not so constant among the temperatures we use. It varies a little bit, but it's the heat transmission. You're going to see this BTU, inches per square foot per hour per degree Fahrenheit. We're going to talk about what that means in a little bit. And here's some refractories in terms of their thermal conductivity value at some temperature. So just focus on 1,000 degrees, and the highest thermal conductivity is that 60% aluminum burning zone brick, that andalusite brick, which is up around 15.5. As you go down to Super Duty fire clay, more porous, less dense, well, it's 9. Keep on going down. Some insulating castable, about 1.25, 2,000 degree insulating castable. So we're getting much more porous, less rugged, less strong, but much more porous, and therefore we have much more insulation. Here's a K23, that's a manufacturer's designation for a 2,300 degrees Fahrenheit duty rating on an insulating fire brick. Here's a K20, which is a little bit different. Go on down here to some granular materials, which are very light in weight. And here's ceramic fiber, 8 pounds per cubic foot ceramic fiber at 1.1, and 8 pounds per cubic foot blanket down around 0.8. So just trying to make the connection that as you go more porous, you're losing strength, ruggedness, durability. So for a hearth, you might have to have material up here, but for just pure insulation, you might come in down into this area right here. Now we're going to do some calculations in a little bit, which we're going to talk about ceramic fiber and blanket products. Okay, now we're going into part B, and part B is going to take us a little while. This is going to be about heat transfer and heat storage in kiln linings. So I'm going to make a suggestion to you. If you have the time, you can continue on with this lesson and go on and complete it. If you don't have the time, there are a pretty good number of slides remaining. You can break this class into 2 different periods. So it's your choice. You can stop at any time and you can review at any time. So I want to remind you that we applied the law of conservation of energy essentially the first law of thermodynamics to our concept of firing in a ceramic kiln. And here's what we had right here. And remember, this is a Sankey diagram of the amount of heat that's going into an enclosure or furnace and the amount of heat going out. So we lose some heat just simply due to stack loss, heating up of combustion gases and the heat coming out the smokestack. We're going to lose some heat due to various other things like conveyance, wall losses, leaks, opening losses. There was conveyor loss right there. And so there's some of this heat is going to go to heat storage. So it turned out that we got a little less than half of the heat into the product in this particular Sankey diagram than we put in. We put in a lot more heat, but it went other places. So we express that, and whether you like equations or not, we expressed it this way. There was the first law of thermodynamics. The free energy, or the energy do work, is equal to the total energy that we put in minus the irrecoverable or unusable energy loss. So I turned the equation around in teaching this course and said the enthalpy that we have to supply is equal to the energy to do work plus the heat losses. So heat required is equal to heat released plus heat storage plus heat losses. Now, of course, you could also put a plus for the materials requirements as well. We're going to do some of that later on. We know that we have heat flow modes of convection, conduction, first convection, and radiation as means of transferring energy, depending on the situation. And there are equations. These are differential equations. The amount of heat per unit time is equal to the heat transferred through conduction equal to minus a constant. That constant is very important. That K is a constant we call thermal conductivity times the area times the change in temperature from hot face to cold face where the heat is flowing, okay, divided by the distance through which it travels. So this is not so difficult. The heat per unit time is equal to a constant times the area it goes through times the temperature change in an area over the thickness. And we like to define a quantity called thermal resistance, or R. You see this in various kind of insulations when you go to the store to buy some insulation. R is equal to the length of travel of the heat divided by the thermal conductivity. So the total R is equal to any individual components, L1 over K1 plus L2 over K2, and so on, as many segments of conduction as you may have. So even though these differential equations look difficult, they're really not. It's just common sense. The heat per unit time is equal to a constant times the area times the temperature change over the distance change. Now there's a negative sign here because the heat is flowing from high temperature to low temperature. So we're just trying to show some directionality of flow here in this situation. Well, the heat loss through refractories is equal in macroscopic form, the Q over area. Remember, we had area over here before, we took it down here. Q over area times time, that would be BTUs per square foot per hour. In our inch-pound systems of unit equal the constant K times the high temperature minus the low temperature over the distance the heat travels. So that's pretty easy to understand. BTUs per square foot per hour is equal to the thermal conductivity times the temperature change, in this case in degrees Fahrenheit, from hot face to cold face over the thickness. Pretty easy for thermal conductivity. Some facts about thermal conductivity. It does change with temperature. And we have enough temperature in industrial furnaces to worry about that change. A lot of cases, people will look at the average temperature. They'll calculate the average temperature in a refractory lining component, and that's the thermal conductivity that they will use in calculations. The reciprocal of thermal conductivity is called the R value. So here we have inch-pound dimensions, BTUs per hour per square foot per degree Fahrenheit, and we can convert it easily to kilocalories per hour per meter squared per degree Kelvin. So that's about thermal conductivity. We know it changes, and we usually use the average temperature. Now, if we have two components, as we typically do in an industrial furnace, if it's not fiber lined, we may have a hard outer layer to resist the environment and a lightweight or insulating material on an inner layer. And so each one has a thermal resistance, okay? So from hot to cold here, we're going to have a temperature 2, the hot face, minus the cold face over R number 1, which is the resistance of the hot face, plus R number 2, resistance of the cold face. The cold face here, we're assuming no heat loss on the cold face, just situation right here. We're going to talk about convection right now. So here's the differential equation for convection. The increment in heat per unit time, the change in heat per unit time is equal to the area times the new constant. Okay, that's the convection coefficient, H, that's typically used in the English language, H, the letter H, times the temperature difference. So the heat flow per unit time is equal to the area times the H times the temperature difference. Of course, we're very fond of putting this A back over here, so we have BTUs per square foot per hour is equal to the H times the temperature difference in degrees Fahrenheit. So you can take this pretty far if you have a multi-component lining with heat loss through two components, an R1 and an R2 resistance, plus a R of convection. You can calculate the R of convection in different ways. So we can calculate the total heat loss in macroscopic form using an equation of that nature. Finally, radiation. Radiation becomes important as we get up around 800 degrees C, 1500 degrees Fahrenheit or thereabouts. We can have enough radiant energy transfer to make it happen. So the Q is equal to a Stefan Boltzmann constant times temperature to the fourth. Okay, so transfer between two bodies comes down here with several constants, including area, times the high temperature to the fourth minus the lower temperature to the fourth. The higher temperature body minus the lower temperature body, and we can calculate that. Now, if you don't like calculations, we got alternatives, and that's what we're going to use in this course because we let the computer do the work. When I was a university student, we used things like the North American Combustion Handbook, which, believe it or not, existed back then. And they have tabulated heat transfer data for different types of products in that handbook. So you can pick a product and pick a hot face temperature and pick a cold face temperature or a given thickness, and you can see how much heat is going to flow through that product. A lot of engineers use that for design for a lot of years. Now we have the Honeywell HALC program, which is going to allow us to do the same thing. I'm going to demonstrate it in a minute. And we have the Morgan Thermal Ceramics heat flow. Now I'm using heat flow 4.0. And you're probably, if you've gotten this available, then you're probably using a later version. So some of the information may have changed a bit from what I'm going to present to you. I want to say that both these systems, we're going to compare them in terms of thermal conductivity calculations. they don't have the same data. The Honeywell Hauck eSolutions has file data in its database, whereas Thermal Ceramics really has data for the products that Morgan makes. And so we don't know that they're the same. They're going to give slightly different answers. Okay. We can expect that. And a few BTUs is not going to make a tremendous amount of difference. You're going to put enough firepower into a furnace to have excess BTUs. Anyway, we're not going to just have the minimum amount of BTUs to accomplish a purpose. So I'm going to show some examples of some heat transfer calculations. Okay, I'm going to start with eSolutions, and here we are. Now I thought about switching over to eSolutions to do this as kind of a live demo, but I'm going to tell you that all through my life I've taken computer training of various sorts, and I've hated watching somebody else manipulate a computer. I just think that's the least effective way to learn. People can criticize PowerPoint if they want to, but PowerPoint really serves as a textbook. And so this way I don't have to manipulate the computer. And so we're in Hauck eSolutions. We're looking at heat transfer from a vertical plate. Okay, so there's a plate that's hot on the outside. We've had to select a fluid for the surrounding atmosphere, which selected air. Okay, we've selected a vertical flat plate. And so the little program shows that we're going to have air that's heated by the presence of the plate here, and the air is moving upward by buoyancy when it's heated. So this is how the Hauck program calculates convection heat loss from a furnace shell. So it's pretty neat. So given those conditions and the temperature that I've chosen in this particular example, which looks like 60 degrees Fahrenheit and a wall temperature of 180 degrees Fahrenheit, remember that you want that wall temperature always to be low enough that you don't scald the human being's flesh if they touch the side of the furnace. Otherwise, you need to protect the furnace, put it in a cage or something so somebody can't touch it. So given those conditions, 180 degrees flat plate with an outside ambient temperature of 60 degrees Fahrenheit for natural convection, that's no airflow against the side, then you can see it calculates 1.07 BTUs of energy transfer per square foot per hour per degree Fahrenheit. Okay, the metric unit is given to you right here in watts per meter squared degree Kelvin. Okay, so that's a whole lot easier than trying to calculate this using equations. If you're an engineer and love to do that, then good, great, you can calculate it. But nevertheless, that's an example of convection heat transfer. Here's out of the eSolutions program, heat transfer from a horizontal plate that might represent the top of a kiln shell. And we have air out here. I've taken the same or similar temperatures. I think I took the flat plate at 180 and the air at 60 degrees Fahrenheit. Chose air as the medium and horizontal flat plate and pressed calculate. When I did that, you can see that the results are right here. My heat loss from that horizontal plate is 1.15 BTUs per square foot per hour per degree Fahrenheit. Here it is in metric terms. So just to compare everything, the vertical flat plate with the same temperatures lost about 1.07 BTUs per square foot per hour, whereas the horizontal flat plate lost a little bit more. Okay, so that's the situation. Now, of course, in a large industrial plant, we almost always have some airflow around the plant. And you're going to find out that eSolutions uses a default airflow of about 2 miles per hour. That's pretty slow. Now, remember, I said that we had to protect personnel from being burned on the outside of a furnace. And so you can look up various resources like this and consult with your safety people, but these are scalding temperatures at which scalding of human flesh will take place, temperatures versus time of contact. And of course, the shorter the time of contact, the higher the temperature a human being can take place without getting burned. But for longer durations of contact, if somebody grabbed a pipe or fell into a furnace wall from the outside of the furnace, they might be there a little bit longer. So typically designers will take into account scalding temperatures, and safety people will take into account scalding temperatures. If they measure a temperature on the outside of a furnace above a certain level, they may require a cage or a protective device to keep people away from that furnace. Now there's some other convection utilities. This is in the forced convection heat transfer utility. And here we've selected a vertical plate in cross flow, okay? Vertical plate in cross flow, okay? With air as the atmosphere, 60 degrees Fahrenheit again, 180 degrees is the wall temperature. And here, we're gonna calculate what would happen at about 15 feet per second, or that's about 10 miles per hour. So we could just press calculate. You'll get the answer. I didn't show you the answer in the interest of saving a little time. But this is a very convenient utility, and this is how the HALC program, Honeywell HALC program, does the calculation. Now, the Honeywell HALC program also has a radiation heat transfer utility, and it talks about radiation heat transfer between two hot surfaces into a load within that's placed between those furnaces. So there are certain geometries here that you can select, and you can come up with radiation heat transfer factors. But it turns out that we're going to let the furnace utility, the calculation utility, do it for us. Now I'm going to show you a little bit about the Morgan heat flow utility. I'm using heat flow 4.0 up here, so that's an older version. And I'm going to show you how to use it. So the first thing you do is click on flow up here once you've launched the program, and then you're going to see a screen that says things like materials and environment. You're going to choose environment, and environment's going to tell you whether you're looking at a furnace wall or crown, whether you're something about your ambient air temperatures and things of this particular nature. Your furnace temperature, it will ask you. And so the first thing to do is click on flow and then click on environment. I like this little utility. Once you've set the environment, then you're going to see a screen like this, and you're going to have different layers. So this particular program allows you up to 10 layers of refractory. An inner layer, which is going to be exposed to the furnace environment, is number one. Then you go toward the outside of the furnace with number two or number three. I've never seen a furnace that took 10 layers of refractory, but anyway, nevertheless, in order to use this, you click on box number one. You're in materials to get this box, by the way. You click on box number one, and then you're going to select a material. And you click on the material that you want, and it will pop up here onto the screen. Now, in my case, my first material is going to be high-duty fire brick. Morgan Thermal Ceramics, to my knowledge, doesn't make high-duty fire brick. There's no data in the database. So I had to add that data. They have an ability to let you add material of your own choosing into that database. So you've got to have thermal conductivity versus temperature data in order to do that. I'm going to ask you to do a homework problem today where I supply you the data and ask you to do that. So I've clicked on the material. It showed up here, and I've entered a thickness. I clicked on thickness and entered a thickness. It looks like I entered 3 inches in this particular example. So a typical fire clay refractory brick is called a straight brick, 9 by 4.5 by 3 inches in dimension. So that's what I did. Then I went on to put my cursor in number 2. I selected material number 2, and in this case, looks like I picked a K20 insulating fire brick. Well, that is a brand of thermal ceramics. K is their designation. 20 means 2,000 degree duty rating. So then I clicked on this third layer, and I added a carbon steel shell for this particular furnace. And once I entered the thickness of the shell and had everything in order, I clicked on the program just about anywhere, and it will instantly do the calculation for the environment that you have picked. And in particular interest, it's going to give you the cold face temperature. It's going to give you the heat loss in BTUs per square foot per hour. If you're choosing inch-pound dimensions, it's going to choose the heat storage in BTUs per square foot in steady state heat flow conditions. So it's assuming the furnace is held at 2,000 degrees Fahrenheit. I believe that's what I used as I set up the program. So nevertheless, I picked a wall orientation. And so given that information, when you click on it, you're going to get the heat loss, heat storage, cold outside temperature. You also get the interface temperature, okay, between layer 1 and layer 2 and layer 2 and layer 3, which was the steel shell. So you get a lot of information pretty quick in this simulation program. Of course, you're able to easily add different velocities. So with the model that I'm using in a wall at 0 feet per second, you can see the heat loss was around 611 BTUs per square foot per hour. If I increase the ambient velocity to 15 feet per second, then I'm going to be up at 636. So that's what happens. And of course, that has a corresponding effect on the cold face temperature. So people have been using air horns or air blowers and other things like that for years if they get a shell temperature that's a little too hot or a hot spot on the shell. Now here's the case of a furnace design, lining design, layer design, which showed the interface temperatures in red. Now I have not put in enough temperature for the super duty fire, the high heat duty fire brick to be something that should be used at the use temperature of this furnace. I'm not too worried about that, but the interface temperature for the K20 here is too high, and it showed up in red, and that's something to worry about because you don't want to have shrinkage in the backup layer insulation over a long-term thermal exposure. So the program is designed to help you understand that particular situation. So the real beauty of this program is it allows you to compare different lining designs and configurations. So for example, I had a comparison of 3 inches of fire brick, 3 inches of K20s, and an 1/8 inch of steel. In this case, I used a 9 inches of ceramic fiber modules with tacked to an 1/8 inch of steel. And you can see the heat loss is dramatically different. Excuse me, that's heat storage right there, 18,000 or so BTUs per square foot, whereas with the fiber, I'm down about 2,037 or thereabouts. So that's the advantage of refractory fiber, little heat storage if you can use it in your particular process furnace. The heat loss with the conventional lining, with the hard brick lining is 611, with the fiber 276. So the cold face temperatures were correspondingly different. I mean, the hard refractory is transferring heat out to the shell, and the fiber is much more efficient at protecting the steel shell. So just remember that we got heat loss and heat storage in a theoretical one-dimensional multi-component lining, heat loss, heat storage, and cold face temperatures. Now we can get the same thing with Honeywell Haupt eSolutions. Okay, we go into the furnace heat loss utility, and we have to set up a furnace, rectangular furnace, and give some dimensions. For this purpose, it doesn't matter too much what the dimensions are. And there you select the refractory type that you're using in the program. And so given that refractory type, I had 2 components in the hearth, which is very common to a hard material with a backup insulating material, and 1 component in the sidewalls and the crown. You can see the thicknesses that I used in this particular calculation, but nevertheless, if you look up at heat fluxes, then the sidewall flux here is given to you in BTUs per square foot per hour. That's the dimension up here that I'm using the program in. You can put it in SI units if you want to. And this is going to give you data for the top, the sidewall, and the bottom. But the sidewall is the number that is most comparable to the one in the thermal ceramics program. And of course, it also gives you the heat storage in BTUs per square foot here. And so for today's situation, it's doing the thermal conductivity calculation to get the values. It's showing you the outside shell temperature right here, the inside furnace temperature, and it shows you the interface temperature if there is an interface there in a multi-component lining. So it does pretty much the same thing, of course, as the thermal ceramics program. You can use it, but to my knowledge, you cannot change the data that's in the database. Whereas with thermal ceramics, you can add data if you want to. And so that's very useful for us. One of the things that is useful about the eSolutions program, it allows you to add air leakage factors in here. So here's an example of the same lining with no openings. I have a wall and hearth loss here, but if I add 5% openings, same furnace, then we're going to see an effect on the wall loss and the opening loss. So the total loss is quite a bit different when I had an open door or a slightly open door in the furnace. I thought that was a pretty cool feature of this program. So, gentlemen, and ladies, this is where we're going. We've introduced you to the modeling capability of heat flow. We've introduced you to the modeling capability of eSolutions. We've talked about thermal conductivity of refractories, the basis in terms of equations that are pretty commonsensical. You can use those to the extent you want to, but back when I took this course many years ago, we had to do all these calculations manually modeling the heat loss through a wall and through a crown atop of a furnace and calculate convection heat loss. And well, you know, it was pretty exhaustive to do that. Quite frankly, when I was in engineering school, we used something called a slide rule to do calculations. We were not allowed to use even handheld calculators, which were available at that time. And fortunately, you have these calculation utilities. So I like to use these utilities because it's really easy for you to answer the what if question. It's really easy for you to model the furnace. And so the next 3 lectures are going to be furnace models. We're actually going to start with a heat treating model because it's pretty easy to understand. We're going to calculate the heat required by the load to get up to a certain temperature, and we're going to hold it at a certain temperature using the furnace heat loss utility. And we're going to calculate the total amount of heat that you have to heat up the material and to maintain the material for the soak period required for heat treating. It was a really simple example. Then the next class, we'll go to an example where there's an endothermic reaction that's pretty significant. In the last class, we're going to compare e-solutions with some real data that was taken in my laboratory. So that's where we're going in the course. There are going to be 3 lectures or 3 classes that deal with the furnace simulation capability of e-solutions. Well, we're going to go there, but I'm going to ask you to do something. I haven't asked you to do this in this course so far, but I'm going to ask you to use the utilities, either one if you have one, or both if you have both, e-solutions and heat flow. And so there's a problem. So here's the problem stated and some conditions for the problem. To do this in PowerPoint so that you could do a screen capture and print these, I had to do several slides. And my problem is going to ask you to add some high-duty fire brick data to the heat loss. So here are the instructions on how to add the data into the heat flow program. If you don't have the heat flow program, then you don't have to do this. You can do the homework using only e-solutions. But if you do have the heat flow program, then in fact you can do it. And here's the plot of thermal conductivity versus temperature for the high-duty fire brick. And you can see that it changes a fair amount over the temperature range of interest from room temperature up to about 2000 degrees Fahrenheit. So that graph may be useful to you. Here's some information about the problem, and here's the problem. There's a number 1 problem using a fire brick lining with insulating fire brick backup, both with e-solutions and or heat flow. Then we're going to do a problem where we use a refractory castable. The brand name for Morgan in my database is Keocrete. 26 means 2600 degree dense castable, 4.5 inches of that. And Keolite in refractory terminology, when they use the word light, they mean insulating castable. That's a 2000 degree insulating castable, 4.5 inch, and you're going to compare that to castable in e-solutions and lightweight castable. That's their terminology. And finally, we'll look at a model which uses a product called PyroStack. That's a module product that's in their database. If you can't find that one, you can use any module. I believe that is 12 inches of refractory, backed by a carbon shell. E-solutions just assumes the carbon shell, so you only have to enter the refractory. So that's your homework. We're going to go over this homework next time. I'm going to provide you with my solutions to this problem. And the purpose of this is to get you used to using the furnace modeling software. So I think it's very useful to ask you to do something. So remember, you can do a screen capture and you can go back and look at these slides and print what you need to print in order to do your homework, problems 1, 2, or 3. So they're pretty easy to do. And so next time we're going to look at our very first furnace model along with the homework solutions. This has been a fairly long class today to cover this subject. I've talked a bit about safety features, freezing of castables, explosive spalling of castables when they appeared to be set but weren't. They were frozen or weren't in a good condition when the drought happened in the furnace environment. I've talked about mortars, typical sodium silicate in wet mortars as an eye burn hazard, and dry mortars, if it's sodium silicate, will be in a solid form, but when you add the water, of course, you've got sodium silicate in the mortar, and that, again, is an eye burn hazard. There are other types of mortars that contain phosphate binders or clay binders. I understand that, but that's something to be certainly aware of. I talked a little bit about respiratory hazards and respiratory protection with ceramic fiber. I talked about heat storage and heat conduction in furnace and multi-component linings. Particularly, I talked about not exceeding the duty rating at any portion of any component because that's going to cause deterioration or shrinkage in the refractory. I talked about ceramic fiber and the fact that it can be susceptible to damage over time. I talked mainly about velocity effects on fiber blanket, but nevertheless, you can see that it can't carry much of a load other than its own weight. It's typically attached by some attachment system to a furnace shell. It's a wonderful material, and I'm sure that your refractory suppliers, including the Morgan people, can be very helpful in getting you to understand the characteristics of the material and the proper use. Remember, with castables, they are not containing Portland cement, calcium silicate cement. Instead, they contain calcium aluminate cement, which is a different chemical, and it's a very sensitive chemical. It's sensitive to the cleanliness of the water and the pH conditions and the temperature. And of course, the properties that you get in castable refractories are dependent on using the right amount of water, even if that doesn't allow the castable to flow too much. I haven't really talked about repair of refractories in furnace operations. I saw a guy with a bucket of castable and a trowel go around and try to patch kill cars one time, and I said, "Why? What's he doing?" I mean, you know, there's not going to be any bond there. I mean, he's just filling up space with solid material. There are other ways to do that. And of course, you can send me an email or ask for a Zoom office hour anytime that you wish. Well, I hope you've enjoyed this, and we're going to get really to the fun part of the course coming up, where we look at the furnace models.